So, greetings, students. So, today's lecture will be dealing with the continuation of the introduction part of your symmetrical components. So, here we have seen about the symmetrical components and why we are in need to get towards the symmetrical components. That is, to convert the system from an unbalanced state to a balanced state, you have to multiply with some vectors. Okay, so these vectors are responsible for making your unbalanced system to a balanced system, and these vectors are called as symmetrical components. If we are changing in a positive sequence, then it comes with respect to a positive symmetrical component, and for if you are changing in the negative sequence, then it comes with respect to your negative symmetrical components, and same goes for your zero symmetrical component. Okay, so this is the representation of your balanced and your unbalanced system, and this is the representation of the phase sequence we have already seen. So for the phase sequence to be positive, the sequence will be around A, B, C, and at the same time, if it is at the negative, it becomes ACB, and for the zero, it will be VA0, VB0, VC0. So over here, the phase angle will be zero, the displacement of the phase angle will be zero, and everything will be in parallel to each other. So we have also seen the diagram. Okay. So with regarding the symmetrical components, so this is regarding the symmetrical components. This is regarding symmetrical components. So for the positive sequence components, so you'll be multiplying with a square VA1, and for VA1 you'll be multiplying with VA1. The same goes, but for VC1 you'll be multiplying with A. Okay. Similarly, for the negative sequence also it goes like that. And for the zero sequence it will be VA0, VB0, VC0. Okay, so now what we'll be seeing is, I said we'll be multiplying with the factor or the vector A, right? So this is A. So now we have to know that what is the quantity A represent? What does A represents? We have to see. So this goes with the definition of operator A. So it is called as operator A. Operator A. Okay. So what does this operator A actually denotes? What does this operator A indicates? Actually, what it specifies? As you know that for converting an unbalanced to balanced system, you'll be making use of this operator A. Okay, so that's the usage purpose. But generally, what this operator A means? Operator A denotes 120-degree phase shift. It denotes a 120-degree phase shift. Okay, so it is a vector. Okay, it is a vector, and now it is representing a phase shift of 120-degree. So if it represents a phase shift of 120-degree, then you can represent that in the form of a complex term. Okay, you can represent it in the form of a complex term. So how you can represent? So A is equal to unit vector e power j120. Okay, so this is the representation. That is what they're saying is A equal to e power j120. So now we are representing this in the complex format, and this becomes cos 120-degree plus j sine 120-degree. Okay, so generally this represents nothing but your uh, phase shift, 120-degree phase shift. Okay, and now this cos 120-degree becomes minus 1 by 2. Okay, it becomes minus 1 by 2, and this sine 120 becomes plus j root 3 by 2. Okay, so this is generally your value of A. Okay, this you can further simplify it to get a value around A equal to around minus 0.5 plus J 0.866. Okay, so I hope you are able to understand. So A represents A equal to e power j 120 degree, which is equal to minus 0.5 plus j 0.866. Okay, this is for A. Then what happens with respect to your A square? Okay, with respect to A square, what happens? For A square, it becomes A square will be equal to e power j 240. Okay, so now what happens? The sign change occurs. So here it will be minus 0.5, and here it will be minus j 0.866. Okay, so this is the value of your A square, and now coming towards your A cube, it becomes e power j 360. Okay, and now what happens? This becomes the value becomes unit 1.0 plus j 0.0. That is it is
Sir,
equal to 1. So A
we see
cube will
on
be
this
the value of
component
your A cube will be equal
parent.
to 1. So these are all the shortcuts you have to know when handling the problem. Okay.
So can you hear me, sir? Oh, sir.
So this is what with respect to your A operator A. Okay, I hope you are able to understand it. And now we
Sir,
will be moving towards the symmetrical components. Okay, that is unbalanced component. How you conversion to a balanced system. So that we will be seeing how to convert an unbalanced system to a balanced system using the symmetrical components. So we will be dealing now. Okay.
சார் கேட்குதா சார் பேசுறது? ஹலோ சார்? சார்?
Conversion of unbalanced system to
சார், can
balanced
you hear
system
me, sir? Sir?
using symmetrical components. So how it is made possible we'll be seeing. So first you have to write the unbalanced voltages. So the unbalanced voltages are starting with your A phase. So VA will be equal to, so it is a combination of your all the three sequences. That is starting with your zero sequence, followed by your positive sequence, followed by your negative sequence. Okay, similarly, this goes for all the three phases. So it will be VB, it will be equal to VB0, VB0 it is, okay, VB0 plus VB1 plus VB2, and this goes for VC, it will be VC0 plus VC1 plus VC2. So this is the representation of your unbalanced voltage. Okay, and now we have to represent your balanced voltage. Okay, for that for that conversion, what you have to do is you have to represent all these things in the uh, in your phase using your term A. Using this operator A, you have to convert all the things through your symmetrical components. So the symmetrical components, what we have seen, are given here. So for zero sequence it's nothing, but for your positive and negative sequence you have to replace your VA1 with VA1, okay fine, and VB1 with A square and VC1 with A. Okay, this is for your positive sequence. Okay, for the negative sequence, VA2 goes similar. VB2 will be A into VA2, VC2 will be A square. Okay, so now to get a balanced one, we'll be replacing it. Okay, so after replacing, so all values in terms of operator A, in terms of operator A, also so if you are putting in terms of operator A, so your VA will be equal to the same thing, VA0 plus VA1 plus VA2. Okay, whereas your VB, your VB becomes VA0. So after replacing it becomes VA0 plus here what happens, you have to replace your VB1. Okay, so your VB1 will be equal to, so over here your VB0 will be equal to VA0. Okay, and then your VB1 will be equal to A square into VA1. So this you have to put over here. So it will be A square into VA1, okay, plus the negative sequence. Okay, the negative sequence VB2 would be equal to A times of VA2. Okay, and this you have to substitute over here. So now what it becomes, VA into VA2. Okay, and the same goes for your VC. So for the VC, it will be for your VC it will be VC not equal to VA naught. Okay, and then VC1 will be equal to A into VA1. Okay, and then VC2 will be equal to A square into VA2. Okay, now you have to substitute this over here. So you'll be getting VA0 plus A into VA1 plus A square into VA2. So now it is evident that we have converted everything in the form of your A phase voltage, right? So now it is corresponding to the zero sequence of the A phase, positive sequence of the A phase, and then the negative sequence of the A phase. We have represented everything in terms of the A phase, so it will be easier for the calculation part. Okay, I hope you are able to get right. So we have completely changed. So here you can see it had VB0, VB1, VB2. Okay, so this entire part has been completely changed in terms of your VA. Okay, using this operator A. Okay, and next we will be representing this equation. Okay, it is a three unknown. Okay, three equations with three unknowns, so it is possible to represent this in a matrix format. So if you're representing in the matrix format means how it will be, means it will be VA, VB, VC, which is equal to, this becomes 1, this becomes 1, this becomes 1, and here comes A square, A, and then here it will be 1, A square into VA0, VA1 followed by VA2. So we have represented the previous equation in a matrix format. Okay. And our ultimate aim is that these voltages corresponds to your balance voltage. Okay, so this voltage over here at the left hand side corresponds to your unbalanced voltage. So this over here at the right hand side corresponds to your balanced voltage. So our need is that we only need the balanced voltage. Okay, so in order to find the balanced voltage, what you have to do is that you have to bring this matrix around to your left hand side. So if you are bringing towards the left hand side, what happens? You have to take the inverse. Okay, so now the balance voltages is got by VA0, VA1, VA2. Okay, this will be equal to this you have to bring it this side, so it will be taking inverse 1 1 1 1 a square a 1 a square, and then you have to take the inverse, okay, into the unbalanced voltage VA, VB, VC. Okay, and after taking the inverse, so you'll be getting the equation as VA0, VA1, VA2. So this will be equal to 1 by 3 into, so 1 by 3 how you are getting means you have to take the adjunct of the matrix. So taking the adjunct of the matrix, you will be getting this 1 by 3. Okay, and then after that you will be taking the transpose. So this will be 1a and then a square, 1 a square, and then followed by the a. Okay, into VA, that is the unbalanced voltage VA, VB, BC. Okay, so this is your approach, the final value of converting your unbalanced voltages to a balanced voltages. Okay, and next we will be seeing about conversion of the currents. The current conversion is also the same, the exact is applicable for the current conversion also. So you have to know about this. And for current, similarly, for current you will be getting, first you will be writing the unbalanced current. So unbalanced current, so unbalanced currents are nothing but IA, IB followed by IC, which is equal to 1 1 1 1 a square a, and then 1 a square into your balanced current, which is nothing but IA0, IA1 followed by IA2. Okay, so this corresponds to your unbalanced current. The same what you have done for your voltage is applicable over here. Okay, and here after this for the balanced current, we'll be getting IA0, IA1, IA2 will be equal to the same thing, 1 by 3 1 1 1 1 a square by 1 a square a, okay, into IA, IB, IC. Okay, so this is the value of your balanced current, and over here A will be equal to 1 at an angle of 120 degree, and then A square will be equal to 1 at an angle of 240 degree. And another thing what you have to know is this 1 plus a plus a square value will be equal to, always it will be equal to 0. Okay, if we are substituting this, you'll be able to get it. Always this 1 plus a square value will be equal to 0. If you want, you can just substitute using that complex power, you'll be getting this. Okay. While doing the problem, this will be somewhat easier for you. And now the complex power. So the complex power is represented as the complex power is nothing but your VA, that is your apparent power. Apparent power S will be equal to 3 times of VA0 IA0 followed by 3 times of VA1 IA1 followed by 3 times of VA2 IA2. Okay, I hope you are able to understand this regarding the symmetrical component conversion. Okay, so this is a very important part regarding the A operator. You have to know how to convert from your A operator, your balanced system, to your unbalanced system. You have to know. Okay. And next we will be moving towards your sequence representation of your synchronous machine. Okay. Okay, next we will be seeing about your sequence representation of synchronous machine. So this you have to know while dealing with the problem. So how to represent your synchronous machine in terms of your sequence, that is your positive, negative, and then your zero sequence. So what happens in this three sequence and how to represent this uh, synchronous machine. So first we have to consider a synchronous machine. So we can take this to be as a star connected. Okay. Okay, so also it is grounded. So there's a fourth neutral point. Okay, so it is grounded. Okay, so this is your synchronous machine. So we can take A, B, and then this to be C, and the voltage over here it will be plus, minus it will be EA. Okay, and over here it will be plus, and then here it will be minus, it will be EB. These are all nothing but your back EMFs. So it will be plus and then minus. So it will be EC. Okay, and followed by here it will be Zn. And now how the neutral current will be over here In. Okay, so now our ultimate aim is to represent this thing in terms of your positive sequence, negative sequence, followed by your zero sequence. So that's what we'll be seeing now. How to represent in your three sequences we'll be seeing. So moving on, first we'll be considering your positive sequence. So first in the positive sequence, what you have to know that the current flow will be only the positive component currents will be flowing. So that alone you have to check it out. So based upon the positive flow of current, how the equation changes you'll be seeing. I should be drawing the diagram. This goes with A, this goes with B, and then this goes with C. Okay, again this will be plus minus EA, plus minus EB, plus minus EC. Okay, so we are speaking about positive sequence. So if it is Z1, Z1, Z1 you can take. And now regarding the current flow, it is a generating quantity, right? So the current flow will be from your uh, generating source, that is towards the load it goes. So it will be going in the outward direction. So it will be IA1, will be IB1, and it will be your IC1. Okay, IA1, IB1, IC1. This is a three-phase model. So this is a three-phase model. In case if you are having a single phase means, how it will be having means very simple. It will be Z1 followed by your EMF EA. Okay, EA. So we have already seen how to represent the synchronous uh, machine in case of a single phase. In the single line diagram, at the initial stage of the second unit, we have seen. The same is applicable over here. So this will be 0, and the voltage drop across this will be VA1. Okay, and then the current flow will be IA1. That is, it will be outward. This is a single phase model. Okay, so now how the equation will be, you can take with corresponding to your single phase, so it will be easier for you to understand. So this will be equal to nothing but your VA1. So your VA1 will be equal to the normal generator equation that you already know. So EA minus IA1 into Z1. Okay, this is the equation what we'll be getting with respect to the uh, positive sequence. Okay, this is the thing what we'll be getting with respect to the positive sequence. Whereas in case of the negative sequence, what happens means there lies some difference. Okay, in case of the negative sequence, there will be some difference. Okay. Regarding the positive sequence, we have to consider with respect to the source. Okay. But in case of the negative sequence, what happens means the source will be excluded. Okay. So if you are considering that with respect to the negative sequence means you'll be getting the same diagram, but the variation is that this source will be uh, shorted. So why it will be? What is the reason for that? Means here we will be speaking about the source side. Okay, so whenever the negative sequence is coming out, so it will be with respect to your load side performance. So I'll be drawing the negative sequence, and after that I'll be explaining. But the only difference is that it will be shorter. The difference between a positive sequence and the negative sequence, that it will be shorter. So the negative sequence, how we can draw means so this becomes your Z2, this becomes your Z2, this becomes your Z2, and this will be your A, followed by this will be your B, and this will be your C. Okay, and over here the current will be IA2, IB2, IC2. So this is your three-phase model. This is your three-phase model, and in case of your single-phase model, the same thing, except you won't be having the source. So this will be your IA2. This is the voltage of VA2, and over here it will be Z. So this is your single phase model. Okay, so now your VA2 will be equal to, so since there is no excitation source, VA2 will be equal to minus of IA2 into Z2. Okay, so this is the equation representing your negative sequence. Okay, also there is a variation with respect to your zero sequence also. So for the zero sequence, you have to consider your neutral point in case of a zero sequence. Also over here also the zero sequence, there won't be any excitation source. B A, B, okay. And here you have to consider your excitation source. So this will be your ZG0, okay, ZG0. This will be IA0, IB0, followed by your IC0. And over here, as I said, you have to consider your neutral point. This will be your Zn. And over here, your neutral current In will be equal to 3 times of your zero sequence component. So this is another one important thing you have to see. So that is this is a very simple concept. Can just see through it. So that is a current entering this is splits up into IA0, because over here you can see. So your IB0 will also be equal to IA0, right? And our IC0 is also equal to IA0. So as per your KCL rule, what happens? The current entering this single node is equal to the sum of the currents, algebraic sum of the currents leaving this particular node. So which is nothing but the additive of these three currents. Okay, so you'll be getting IN equal to 3 times of IA0. Okay, and next coming to the single phase model. So a single phase model, how it will be means. So here they have considered your ground impedance also. Okay. So what happens? This becomes ZG naught, ZG naught, and into, and over here you have to consider the ground impedance. So 3 times of Zn. Okay, and over here it will be Ia0. This will be your VA0. Okay, so your final Z0 is nothing but the summation of these two things. So Z0 will be equal to G0 plus 3 times of Zn. Okay, and now the final value of your voltage we are representing in the single phase means your VA0 will be equal to minus of, okay, minus of Z0 into IA0. Okay, so this is the formula you have to know regarding the representation of a synchronous machine in three phases, three sequences. So this is for a negative and this is for a positive. You have to be sure that only for the positive sequence you will be having your excitation source, whereas in case of the other two, 0 and the negative sequence, the excitation source will be absent. Okay, and in the upcoming class we'll be seeing the representation of this sequence representation with respect to your transmission line. Okay, I'll be just saying with respect to transmission line as well as your transformer also we will be seeing in the upcoming class. Okay. And